X-ray diffraction methods measure the interference pattern produced by the coherent scattering of an incoming monochromatic X-ray by a three-dimensional periodic graded material, here the crystal lattice. For a specific crystal lattice, constructive interference, peaks of scattered X-rays in the diffraction pattern, takes place only at angles defined by the specific repeat distances of the lattice. As seen in the previous lecture, Bragg's law defines this relationship. X-ray diffraction experiments can be conducted on single crystals, but also on powders. Powder diffraction has the advantage that mixtures of phases can be investigated relatively easily and no relatively rare, well-formed crystals are necessary. Instead, in powder diffraction, the original material is ground very finely and mounted on a sample holder. The powder mount consists ideally of crystalline particles in completely random orientation. If the orientation is truly random, then for each characteristic repeat distance d, there are many particles that satisfy the Bragg law. Flat powder mounts are usually measured in reflection or so-called Bragg-Brentano parafocusing geometry. In this geometry, the incident beam from the line focus of the X-ray tube diverges until it is reflected by the sample. The diffracted beam then converges from the sample and is focused at the point where the focusing circle and the goniometer circle intersect. Here, a receiving slit is positioned to filter out any unfocused radiation. A secondary monochromator can be used to ensure that only elastically scattered radiation, this is radiation that has the same wavelength as the source, is allowed to enter the detector device. The latter measures considerably improve the angular resolution. This will make peaks become narrower, thus showing less overlap with other reflection peaks. Various Bragg-Brentano configurations exist. In the θ-θ system, both the X-ray source and the detector system rotate simultaneously along the goniometer circle. The sample stage in the center of the goniometer circle is fixed. Thus, if the angle between the surface normal and the incident beam has changed by θ, in fact, the angle between the incident and the diffracted beam has changed by 2θ. The peak to background intensity and the peak resolution are the most important parameters to assess the quality of a diffraction scan. Increasing the peak to background ratios can be done by increasing measurement times, increasing X-ray source intensity, or decreasing background scattering intensity. To improve the quality of the XRD data, several so-called optical devices are used to focus, collimate, and filter the X-ray beam. Solar slits, divergent slits, anti-scatter slits, and/or receiving slits are all used to condition the beam and remove background noise. Increasing the peak resolution often involves cutting a part of the incoming and reflected intensity that leads to peak broadening and thus reduces overall peak intensities. Thus, in practice, a compromise needs to be found among different data quality measures, also taking into account practical considerations such as the available time for measuring and the acceptable sample exposure time. Finally, in practice, if we look at an X-ray powder diffractometer, it looks a lot like in these pictures. On the left side you can recognize the X-ray source or the tube, in the middle the sample stage, and on the right hand side you see the detector. In between source and sample and detector, optical devices are positioned. The X-ray tube requires cooling and is usually connected to an external cooling circuit. The high voltage generator for the X-ray tube is usually positioned underneath. During the experiments, the X-rays are shielded off by a leaded casing or lead glass to protect the operator. Before you start data collection, it's important to check if the diffractometer system is well aligned and that a suitable measurement configuration is chosen. In case of a flat plate reflection geometry, a correct combination of optic elements and sample size should ensure that neither sample transparency nor beam overflow at low angles occur. Data collection strategies should aim at collecting a maximum of useful information from the sample. Therefore, the data collection range for Portland cements is usually chosen to be within, let's say, 5 to 70 degrees to theta for copper K alpha radiation, but it can be wider or more restricted depending on the problem. The 5 to 70 degrees range provides key information on hydrate phase reflections at low angles and covers the most intense reflections of both anhydrous and hydrate phases. For most in-house diffractometers, a step size of about 0.02 degrees to theta is used, and the counting time per step is usually a compromise between the optimal signal-to-noise ratio and practical considerations such as the available time for measurements or acceptable sample exposure. The development of high-performance X-ray detector systems in the last decades has allowed to actually drastically reduce measurement times and thus to minimize exposure times of hydrated samples to a couple of minutes. It is advisable also to spin your sample in the horizontal plane to improve the particle statistics of the measurements when doing powder diffraction. This figure gives an example of the dependence of data quality on the type of radiation and equipment you use. Here a comparison is made between the diffraction patterns of two different Portland cements, one measured by a lab diffractometer and the other by a synchrotron XRD. The main advantage of using a synchrotron is the much higher monochromaticity and the intensity of the X-ray radiation. This greatly improves peak resolution, enables much shorter data collection times. And this is useful, for instance, for early-age cement hydration experiments where you want to have very short experiments, measurements, for instance, a couple of minutes. You can discover the insights of a real lab diffractometer in this demonstration video. The video will also show you the operation of the machine during an X-ray powder diffraction measurement. So please have a look at the demo.
Hello, I'm Dr. Xuren Ni, and as Zubin introduced, I will do the demo videos. So here is our Panalytic Expert XRD diffractometer. The X-ray was generated by the X-ray tube. Here we are going to use the characteristic radiation from copper. The X-ray tube is cooled with cooling water. The power of the X-ray diffractometer was determined by the power of the tube and the processing of the detector. Ideally, the more powerful, the better. Typical laboratory X-ray tube is working at 45 kilowatt and 40 milliampere. Unfortunately, the age of the tube is limited because of the decay of the intensity, typically 10% per year. X-ray passed through a set of opticals onto the samples, then was collected by the detector. The K-beta filter, namely the nickel filter, is used to remove the K-beta radiation. The set of metal plates called solar slit removed the most diverging X-rays, leaving the more parallel X-ray to pass. A mask is used to control the length of the X-ray beams, which is related to the size of the sample holder. Another important slit, called the divergence slit, is used to control the width of the beam, which is related to the angular resolution of the pattern. The smaller the divergence slit we used, the higher the angular resolution. However, the intensity of the diffracted X-rays will be decreased when smaller divergence slit was applied. Sometimes, the beam knife just on top of the samples will be applied to remove the scattering of the X-rays at lower angles, which is important to the sample presenting peaks at lower angles. Some of the sample stages are equipped with a sample spinner, which rotates the sample during the data acquisition. Whenever the spinner is available, it is recommended to spin the sample to improve the statistics of the particles. The configuration of the XRD are mainly to optimize the X-ray beam to give the highest intensity and the required angular resolution. At the same time, the beam overflow and scattering at lower angle should be avoided. a range of 7 to 17 degrees of 2 theta using copper radiation for the data accuracy is usually enough to cover most of the peaks for cement-related samples. The scan speed can be wired from lab to lab, depend on the power of the XRD. Typically, 30 minutes of scan within the range of 7 to 17 degrees is good enough to perform the retrieval analysis. While for fresh disks, the scan should be acquired within 15 minutes to prevent the drying and the carbonation of the fresh samples. For some specific cases, such as the comparison of polymorph of tricalcium silicate, enhanced angular resolution and peak intensity for selected range of the pattern can be more useful instead of the full pattern.